So I now will talk about periodic measures. And this, the content of this paragraph is quite abstract, but I suggest you to see this just as a glossary, so just a list of definitions and good notions which allow to organize the theory of periodical functions. So here QP will be the field of periodic numbers. So we fix evaluation V on QP. So normalized by the usual way and denoted by X P, the absolute value associated to this valuation. So a Banach QP vector space is by definition a QP vector space B equipped with norm we will denote just by norm B, which should be non-Archimedean. So the norm of X plus greg is bounded by a maximum of two norms. Which is compatible with the periodic norm on QP. And such that B is complete. So if we have a Banach vector space, we can form the set of elements where the norm is less or equal to 1 we'll call this subset unit ball. And from the definition, it follows that the unit ball is a ZP submodule of B, and beta is a ZP lattice. So we'll say that a family of elements of B is a Banach basis of B if and only if first, all elements lie in the unit ball. So I is an arbitrary set, and such that each element X can be written by a unique way, as an infinite sum No, infinite.
Infinite.
Yeah. So I will explain this notation, which also defines the notion of convergent series here. So by definition, this means that for any epsilon, the set of coefficients AI such that the absolute value of AI is bigger than epsilon is finite. And so the following property will really be used. It appears in.
Sorry, you also might say that X is the only limit point of the set of all finite subsets.
Yes, yes, but just I prefer not to talk about the topology of finite subsets. So yeah, you're right. So the following property can be proved quite easily and explains that each Banach space has a basis. So such a family is a basis if and only if. First, we should require this property, the first property. And the second property is that the system of residues EI bar, where EI bar is the image of EI modulo P B0. Is the basis in the usual sense of space B0 mod P over the finite field Fp. So all this story is just to give one really new example of Banach space. So our main example is the space which will be denoted C ZPQ QP of continuous functions from ZP to QP. The norm is defined as a subnorm, so ZP is compact, so it is well defined. Or remark. So here one can replace QP by a finite extension over QP. So maybe can be infinite but complete. Now, here's the following theorem. I'll look for a number. Theorem 9.
Why cannot the norm be supreme?
ZP is compact, yeah.
Is always a Banach basis? A Banach basis always exists.
Yeah.
In general.
Yes, but
Yeah.
here, I think in general you need the axiom of choice to have a basis of that guy, or FP, you need the axiom of choice.
Yeah. So the theorem 9 was proved by Mahler. It says that the family functions, binomial functions, which are defined explicitly by the usual formula, but x is a variable for n bigger or equal to 0, is a Banach basis of this space.
Is it true also for arbitrary n? Is it true if instead of kp you take arbitrary n?
Yeah.
With alpha n places.
Yeah. Okay, so I will sketch the proof. So consider the space of functions f, which can be written as a power series, not power, a series of the following form. There an goes to 0. So it's easy to see that each function of such a form is continuous. Oh.
Is it not just follow from Stone-Verge theorem?
So, I don't know, I think it's something really elementary because this is a non-Archimedean topology and an goes to 0, so it's a very easy. And also it can be easily checked that B is a Banach subspace. So the only non-trivial thing is the equality of these two spaces. And one can remark that here, so I will denote by 1u the characteristic function of a subset U of Zp. So this is 1 if x is in U and 0 elsewhere. So this function is continuous because in the periodic world, locally constant functions are continuous. So it's a continuous function.
U is open.
If U is open, yes, continuous. If U is open. Okay. Oh, consider the following formula, which I will look first in a pure formal way. So z here is a fixed periodic number, x is a variable, so we write it like 1 plus z minus 1 at x. And now we can use the binomial expansion to write this as z minus 1 n xn. And this formula has a sense if z is a principal unit. So here I will do some thing which I won't really explain. So I said that we can replace here QP by a bigger field and do exactly the same things. So here I will implicitly use this. So I need to take Z not in ZP, but in a bigger field. So we'll just remark that the characteristic function of a set of a form, say I plus Pn Zp of x can be written as the sum of z minus I zx, where z runs all Pn fruits of unity. So the explication is that if x lies in this subset, then we have one here, and we divide it by Pn. So if x lies in this open subset, when we have 1 everywhere, we divide by Pn, so we obtain 1. And if x is not in this open subset, then we have here some sum of roots of unity, which is 0. Non-trivial sum of roots of unity or sum of root. So we have this thing which explains that if we use the previous formula, that this function is contained in B, because z at x is expanded by such a way so it is contained in B. So we obtained that locally constant functions are contained in B, which is contained in the space of continuous functions. But locally constant functions are dense in the space of continuous functions. And therefore, we have an equality. Now we define the notion of a periodic measure. Periodic measure is a continuous linear map mu from the Banach space of continuous functions to QP.
So it has QP values.
Yes. Periodic means periodic value. To keep some analogy with Archimedean integration, we will write this map as integral. But we'll see that here there are absolutely new things which happen. And I mean, the problem is here, because the complex valued measures are well studied. We have the notion of Haar measure on the compact group and the complete theory. But here we want to consider periodic measures, and this is absolutely different thing. So I'll give some example in a few minutes. And just to start, we can see that Mahler's theorem allows to describe all measures very simply. So let mu be a periodic measure. I will denote these measures by using this notation. Periodic measure. Then one can associate to it the following formal integral, I mean formal power series, which will be defined as an integral. So this is the integral of 1 plus t, where t is just a symbol at x, where x is a variable mu of x, and by definition we take the binomial expansion of this thing, and this is equal to the following power series. So this power series encodes all integrals of the basis, canonical basis given by Mahler theorem of all values of a measure on the basis Euler's basis. So it completely determines the measure. So it's a power series. Let's just understand where does it live. Since a measure is continuous, so its values on the basis are bounded. So this lives not really in the Iwasawa algebra, but the denominators can be controlled. So this is a tensor product of the Iwasawa algebra and QP. This power series is called usually Emis transform. Of mu. And it's clear that if we fix a series here, it determines a measure. So we have an isomorphism between the space of measures and the ring of power series with bounded coefficients, so given by a mistransform. Here are some examples. The simplest example of a periodic measure is a Dirac measure. So fix a point and denote by delta A the map which to each function associates its value at this point. Oh, it's easy to see that the mistransform of Dirac's measure is the power series 1 plus t at A. So, the second example explains really the problems with periodic integration. So maybe explains the main conceptual problem of a periodic integration. So we can look for periodic Haar measures, for periodic NLX. Of Haar's measure. So our measure is an invariant measure by definition. So assume that mu for to start, mu will not be a measure in the sense of a definition, but just a map defined on the family of open sets of Zp with values in Qp, which is invariant in the sense of by translations. So if mu is invariant, by translations, so we can start with mu of the whole Zp, and next to write Zp as the union of classes of the form A plus Pn Zp. There A runs all integers between 0 and Pn minus 1. So if mu is invariant, this should be, so first it should be the sum of mu of A plus Pn Zp. But if we want to have an invariant measure, we should have the same things here. And finally, Pn times the measure of Pn_Zp. So if we look for an invariant measure, we obtain that mu at Pn_Zp should be and the problem that this number, as periodic number, doesn't go to 0, so it goes to infinity. Sorry?
Mu of the P is not 0.
Yeah. And therefore, if we can sure define such a measure on locally constant functions, but we cannot extend it by continuity to continuous functions. So this explains why periodic measures are defined just so like linear maps. So we had the following theorem, which can be proved by standard arguments. Let mu be an additive bounded function from the set of open sets, subsets of ZP with values in QP. So then,
That is, you mean disjoint unions are independent?
sorry?
For disjoint union.
Yes, yes.
Finally.
Additive and disjoint unions, yeah. Then mu can be extended by a unique way. To a periodic measure. Now I will state without too much proofs several useful formulas which will be used to construct periodical functions. So the first property is about the multiplication of a measure by a function. So assume that mu is a measure, periodic measure, and assume that we have a periodic function, continuous periodic function, so we define the product G mu as the following measure. So by definition, if we want to integrate a function f against this measure, so we just integrate the product of functions against mu. Simple definition. So the formula which will be very useful is the following. For any measure, the emise transform of the product of this measure with the function xn is dn a mu where D is the logarithmic derivative with respect to t. The next formula if Z is such that that satisfies this condition, then the integral of Zx mu x is the mistransform evaluated at z minus 1. So here we'll need only to replace t by z minus 1 in the formula for the mistransform. Last property, which is quite technical, but I mean, so it seems technical, but we'll see that when we pass to the construction of p-adical functions, here will happen something important. So this is the notion of the restriction of a measure. So I will define it in only in the situation which will be used Friday. Let mu be a measure on Zp, and let U be an open subset of Zp. Then, by definition, the restriction of mu on this open subset. So how we can restrict a measure as a linear map? So we need to kill the functions which we are going to integrate outside U. So this means that in our terminology, this is the product of mu with a characteristic set of U. So this is again a measure on Zp. And we want to compute its emis transform. I will do it only in the following situation. So for any measure mu, the emis transform of the restriction of this measure on Zp star. So we are interested only in the restrictions of Z measure defined on Zp on Zp star, which is inside Zp. So it is given by quite complicated. So I'll write a formula. It's not so easy. So this formula involves two operators, which I will define just below, which will be called phi psi applied to the emis transform of a measure. So where the operator phi is the following. So we define phi psi as operators acting on power series. So the both operators will act linearly. So phi acts on T as follows. So here the thing to remember is that phi acts on T by this way. And psi also acts linearly. Sorry. Here it's not so. No. Here I should be more careful. So I will define the action of psi on the power series F. This is 1 divided by P, the sum over all P fruits of unity Z of F Z1 plus T minus 1. No. Here that's okay, yes. Yes. Thank you. So
obtain something which is a coefficient.
in fact, the coefficients are always in QP.
Yes, but if you have a series in T, you can substitute into it any other series that starts from T but has no zero coefficient. But you have here, you substitute into series something which has a free coefficient. It is not good.
No, because this is a periodic unit. So periodic unit is converged to zero.
So this is
The periodic unit.
yes. So you use here periodic convergence.
Yes.
So it
Yes.
Is, so you use
Yes.
here periodic topology. It's
Yes.
not a formal substitution.
No, not really. So in fact, one can explain this by several other ways. And these formulas appear in quite different contexts. So for example, if you are interested in the structure of local units of periodic fields, of units of periodic fields, these formulas appear too. So this is a relationship of, in some sense, two words. So we see here that there is a relationship between periodic measures and the Iwasawa algebra, because thanks to Amis transform, periodic measures correspond to power series. And so one can precise this analogy, and finally one can relate periodic measures with a structure of groups of units of local fields. And in this theory, these operators appear in a different context. So maybe I will sketch something about this Friday. Yeah, but
sorry, but if you combine, if you apply first psi and then phi,
yeah.
then if you apply phi to this, wait, no, if you, yes, it is.
There is another interesting thing.
Yes,
So
it is, yes, it becomes very, very.
if you apply in this order,
In this order, then it is something trivial, yes. It's identity, yes. But in this order,
Yeah.
it is, yeah, exactly. This order is something.
I'll stop here. So the Friday I will start directly with the construction of periodic functions, Dirichlet functions.